Okay, so today we're going to speak about greedy algorithms. And greedy algorithms are best maybe described by an example. So the basic idea behind the greedy algorithm is that you want to do right. Locally, you want to do right. And there's nothing wrong about doing right, but somehow acting impulsively and doing right locally without thinking the whole thing out is not necessarily the best strategy, both algorithmically and in life. And there are many cases where you do the greedy thing and it doesn't work. In fact, greedy algorithm 99% of the time don't work. There are some cases that they do work, that's why we are teaching you those algorithms. But most of the time they don't work, and they are by far the most natural algorithms, but they are not always, while they might feel intuitive and right to us, they might not be right overall. So that's the first thing to see about this problem. And as an example, let's look on the problem of vertex cover. So this is one of those problems that the name was designed to confuse people. So I give you a graph, and the task at hand is to pick a subset of the vertices such that every edge is adjacent to one of the vertices you picked, right? So you have to pick vertices that guard the edges, all the edges, right? There's always a vertex cover because you can of course pick all the vertices in the graph, but we would like to pick as few as possible. It's a very easy problem to define. It's a natural problem, and it's kind of the easiest guarding version of a problem you can think of. And if you think about it a bit, you would like to pick guards that see as much as possible, that give you cover as many edges as possible. So the most natural thing is to pick the vertex that have the maximum degree, right? So greedy vertex cover, repeatedly pick the vertex of highest degree. It guards all the edges adjacent to it. So we're going to delete the vertex and all the edges adjacent to it, mark this vertex as being in the cover, and repeat this process until there are no edges in the graph. Right? So let's see an animation of that. Right, so you pick this vertex because it has degree 3. After you delete it, you are left with 3 edges, and then it doesn't really matter what you do. You pick a vertex from every edge, and that's it, right? And you go back to the original graph. The algorithm picked all the green vertices, but in fact the optimal solution was the red vertices, right? So greedy algorithm didn't work here. In fact, he picked 4, but the right answer is 3, as one can easily verify. So clearly the greedy algorithm is not the right algorithm here, although it felt very natural, right? Okay. So we cannot do better than a 4-third approximation. This means that, in the worst case, we will return a factor of 4/3 larger set than the optimal set. But it turns out that you can do that the situation is much, much worse, right? In particular, one can show the following theorem, that there is a graph with n vertices such that it has a vertex cover of size k, but the greedy algorithm returns k log n vertices. So it does significantly worse than the optimal solution. The proof of this is outside the scope of this class, so I'm not going to prove it. If you want, you can try and do it. It's a doable, you can try and come up with the graph for which this has happened. I'm warning you in advance, this is a very hard problem. This is not easy, but if you have an hour and you want to think about it, you're welcome to do so. It is a nice exercise. And this is not a coincidence, of course, because this problem turns out to be really hard, right? So vertex cover, simple as it is NP hard. NP hard means that we believe that any algorithm that solves it exactly requires exponential time. So, so the natural greedy algorithm of pick the best, the highest degree vertex is just the wrong strategy. And in some sense, the fact that the problem is NP-hard says that no simple strategy except brute force enumeration is really going to solve this problem, which is very bad news. But in real life, you need to solve this problem, right? Your boss comes to you and tells you, oh, program solve this problem, or, it's somewhere buried inside the program you're maintaining, you need to solve it. You're not going to tell your boss that the problem is NP-hard. They couldn't care less, right? So then you have to program something, and you want to program something fast. You would probably implement what I just described. There are, in fact, other simple algorithms that do much better, but, I don't want to go into that because it's outside the scope. But it really nicely demonstrates the problems with greedy algorithms. They feel right, they do kind of okay, but they're not right. They don't really solve the problem in a lot of cases. Okay, and we will get into more formal definition shortly.